Oh, you're right. Yeah. Yeah. Sorry, I have a few more questions. Is combustion always exothermic?
Yes.
It's always, and the
Yes.
thing that's being, or like the methane or like the methane, it's always like also releasing
Yes.
energy. Okay. Yeah. Okay. Thank you.
Okay. Hi.
Why do the gopher borrow his friend's pants?
Why?
Because he doesn't want to play water.
Is freezing exothermic?
Yes. On the quiz, no. It's okay, don't worry. Come tomorrow, it's all right. Yes. You can look at them, yeah. Maybe not like right this minute, but yeah, we'll have some time later on. Sometimes you are given the concentration and volume of one aqueous substance A, and you are asked to find the concentration of another aqueous substance B in a reaction. This is very, very typical for acids and bases. We do this all the time. There's all sorts of other aqueous things we can use this with, but that's the most standard sort of basic one we start with. Basic, haha, no pun intended. Ha 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 ha. Okay. So, as always, you know some stuff about substance A. What are you going to find? You know probably the volume and the molarity of substance A. Dietmar, could you get the door for us, please? There's noisy people in the hallway. Imagine that, noisy people somewhere other than in this room. Shocking. Yes? You may go get it, yes. So if we know the volume of A and the molarity of A, what does molarity of A mean? Moles per liter. And the volume would probably be milliliters usually, okay? What are we going to be finding? What's the very first thing we're going to find? Moles of A. Stoichiometry? Really easy. All you ever do is you take whatever you're given and you convert it into moles. Once you have moles of that thing, what do you do with it? Turn it into moles of the other thing. So the first two steps are essentially always the same. Find the moles of A, find the moles of B. Find the moles of A, find the moles of B. Find the moles of A, find the moles of B. That's all you're going to be doing. Unless we give you moles of A, in which case you can skip the first step, right? So find the moles of A, find the moles of B, and then from there you can just solve whatever else is given you in the problem. The only thing that's different here about what we've done before is that our last step, so we have begun with the volume of solution A, we found moles of A using the molarity, we found moles of B using the mole ratio. In the past, what we've done is we found the volume of solution B. Yes, using the molarity, that's all nice, well and good. But in this case, we're not finding the volume of solution B. We are going to find the concentration of B. And what we know is we know it's moles. So to find concentration, remember, we take the moles and we divide by the liters. So this has to be given in the question. The liters must be given in the question. So that's the only difference. It's like convert, 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 divide. Okay, instead of convert, 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 convert. In fact, just convert, convert, divide. Not so many conversions. So here we have a lovely neutralization reaction. Could you tell me the name of that acid? Tell your partner, what is the name of that acid? That is indeed sulfuric acid. It is reacting with sodium hydroxide, giving us water and sodium sulfate. We are told that it requires 15.6 milliliters of 0.2 molar sulfuric acid. So that is a complete set of information that will allow us to find what? Moles of A, which in this case is H2SO4, right? If you have volume and molarity, you can find moles. And then we are told how much it requires that much to react with a 25 milliliter sample of NaOH. Calculate the concentration of NaOH. So if we want to do our little solving, H2SO4 is substance A, right? We're finding moles of substance A. From our balanced equation, we know that it takes, where did it go? There it is, 2 moles of NaOH for every 1 mole of H2SO4. So we have 2 moles of NaOH for every 1 mole of H2SO4. At this point, we're converting from moles of A to moles of B. Okay? There's our lovely little string. We found our moles. And now we want the concentration of NaOH. Remember, if you want to represent concentration, you use these lovely square brackets. Those square brackets mean concentration in moles per liter specifically. Just take your moles from here and divide by your liters. And that's it. Here's the one place people make mistakes. Make a mistake. What is wrong with this? Yes. Okay, we'll put that in there. Still wrong. What's wrong with it? Chat with your partner. I'll come back to you. I want to know what's wrong with the work I'm showing. I want to know what's wrong with the work I'm showing. Yes. It's not equivalent. All of this stuff, la 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 la, la la la, la la la, la 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 la, that's all equal, yes? My moles of NaOH is equal to this one times that one times that one, which is equal to the 0.00624. But it is not equal to 0.00624 divided by the liters, and that's where people go wrong, is they will stick that in the equivalency and it's no longer equivalent. You can't just say, it's like saying 3 times 4 is equal to 12, and now I'd like to divide it by 6. Right? Like, you can say, I have 3 times 4, I get 12, and now I would like to take 12 and divide by 6, which would give me 2, but I cannot say 3 times 4 equals 12 divided by 6 equals 2. That just does not work. Does that make sense? So you can't throw a division in there and have that equal sign. You need to do it on a separate line, okay? Now, there is another way to do it. If you don't want to do it on a separate line, you could say, I want to find, instead of finding moles of NaOH, I could say I want to go directly to concentration of NaOH. Okay, so now I'm finding my moles per liter. Okay, 0.0156 liters of H2SO4 times 0.200 moles H2SO4 per liter times 2 moles NaOH per 1 mole H2SO4 times, because at this point what I've done is I've canceled this, I have my moles of NaOH. I can at this point say times 1 over 0.00624 liters. I can do that. It just puts it in the denominator. Or the other way you could do it is you could be like, whoops, sorry. If you're like, I don't get that, you could be like, I am just taking all of this and I am putting it over 0. Well, that was the wrong number anyway, 0.0250 liters. I'm sorry, was it the wrong number that was throwing you? Yeah, okay, okay, sorry. So you can do that, or you can put this, if you didn't have this, like let's just say that was gone, you could take this and put it over 0.0250 liters. That's also okay. Either one of those works, or you can do it in the 2 steps like we did up here. Is good. Just don't put it all in one line. That's the only thing to watch out for. Oh, here it is all in one line. Yes? Titration. Titration is fun. Okay, we're going to learn how to do this. We might even do one on Friday when we have some time to do a lab, because we've got a long period Friday, right? One lab procedure that is used to find concentration of a substance is called titration. It is an effective way to determine the concentration of an aqueous solution using the math like we just did. You gradually add one reactant to the other reactant until magically a color change takes place, telling you that the reaction is perfectly complete. Okay? You haven't added, like if you have an acid and a base, it's like, oh, okay, if I have 10 moles of acid here, and it's supposed to react with 10 moles of base. I drip in 1 mole of base and it doesn't change. I drip in 2, the color doesn't change. 3, 4, 5, 6, 7, 8, 9, 10. And then boom, guess what? It changes color. And by measuring the volumes, we can then figure out our concentration. Would we like to see a demonstration? Okay. Oh, and in fact, while we're doing this, you guys could learn how to use a pipette, because you need to learn how to use a pipette safely. Okay? On the back shelf, you're going to go get yourselves a pipette pump. It looks kind of empty. I might have to grab some more. It says pipette pump. The label is green. I don't know if you guys are listening to me or not, so I can't tell if you're going to be able to do this safely or not. Okay. So you're going to get a pipette and a pipette pump. Okay, they're here. And I guess I will need to get more. But you can share, okay? Like get one for every 2 or 3 people, and then just take turns. Okay. Now, this is one of 2 things where I've had a major injury. Okay. It should be easily avoidable, and yet, where's my step stool? I want to get up high enough so you guys can see me. Look at me, all tall and everything. Okay. The way to break this and send broken glass slashing across the palm of your hand and blood dripping everywhere and having to go to the hospital and get stitches, the way to do that is to hold it down here and hold it here so it's like, you know, there's a lot of breaky bit in between, right? And to jam it on there. Just do that and you too could have an emergency trip to the ER. Okay, or you could hold it up here because it's really hard to break when there's not like a big long area, and you could just twist it in and not have any problems whatsoever. So to be honest, it's not actually very dangerous unless you do it wrong, right? You're in no danger of cutting yourself by doing this. You are in danger of cutting yourself by going, bah, okay? Don't do that. One of my best students ever was one of the ones who like did that. You know, one of those people who like really, really smart, but like the whole common sense practicality, not so much. And you're like, okay. Okay, watch with me. There are 3 controls. One of them is not really a control. There's 2 controls. One is this little wheel here. If you roll it, this goes up. What do you imagine happens when you do that? Suction, yes, okay. If you want to release it, you have 2 choices. Don't do this one unless you're just rinsing it out. It's not meant to be used that way. Okay, so you're going to suck up the liquid. When you want to release it, you are going to press the lever. Okay, what are we pressing? The lever. Did we all see it? The lever. Okay. Now, what's going to happen is when you do this, if you put your pipette right on the bottom, you might not actually get good suction because you'll like have blocked it with the bottom of the beaker. Yes? So you don't have to like really touch the bottom. You can just do that and suck it up, and you'll notice that it goes quite slowly in the middle part. Okay? There is one line on here. All right? It is a volumetric pipette. There's one line on here. Okay? And what I generally do is I suck the water up past that point. And the reason I do that is because, and I'll let you, when you do this, play around with it a little bit so you can watch the phenomenon. I'm just going to show you guys here, and you're going to describe it to people. What happens to the water level when I lift it in and out? It goes up and down. So when I lift it up, the water level actually drops. Do you guys know why? Chat with your partner. Why does the water level go up when it's in and down when it's out? Wow. Okay, do we have any ideas? Yes? I'm putting it in the water, and the water, and the water. I love that. That's a great explanation. Yes. What were you going to say? Because there's air. Where is there air? Somewhere here. Is there air like all the way up to the top of the atmosphere? What's the air made of? Particles. What do particles do in the force of gravity? They pull down. And when they pull down, what do they do to the surface of the water? They push it. And so what's happening is that the water is being pushed down and forced up into here. When I bring it out, there's no longer that pushing up. Okay? So yeah, if I was able to squish it even more, it would go up even more. Yeah, the water pushes the water. So the air pushes the water, and then the water pushes the water up. So yeah, you're kind of right. The water pushes the water, and the water, and the water. Yes. Okay? So all of this theory goes to say, if you want to fill it up to the line, you're not going to fill it up to the line and then take it out, because that will leave you with not enough, right? Because it will go down and you'll be below the line. Fill it up to above the line and then gently roll it down with your eye level with the line, the calibration line. Okay, very nice, very nice. I have to take off my glasses because my eyes are old. You guys shouldn't have to do this. But you don't need to wear goggles because it's like water. Now, if I were to do this and I were wanting to transfer it into another container, would it be okay if my container were way over there on the other side of the desk? Watch this. No. What just happened? There's water all over, because when I go like this, but you can see now there's air bubbles in there. Can you see the air bubbles? Yeah. Okay, that's because when I walk like this, or even if I just walk normally and it bobbles around a little bit, stuff comes out and then air goes in. So you want to make sure that whatever you're putting it into, you have right next door, right beside it, okay? So that you can get it to the right point, and then you just move it over gently, and then you, what do you do to release it? The lever. Ooh, look at that. And then you just wait until it is done. Super exciting. La la la. La 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 la. La 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 la. Huh? I suppose you could do that. But what if you have an acid in there? What if you have an acid or a base? God bless. Okay, now I would like you to tell me what you see. No, no, it's okay. It's water. Water. Okay, what do you see at the end of that? See a line. What's that line? Yeah, there's a little tiny bit of water left. Okay? And you'll know, if you don't get a chance to see it, you'll see it when you do it yourself. There's a tiny bit of water left. This particular pipette, this brand of pipette, is not meant to deliver that extra little bit. Right now, I have delivered exactly 10 milliliters. If I do like this and get rid of that extra little bit, now I have more than 10 milliliters. Okay? When you get to university, you're going to have to ask your professor, your instructor for the lab, what kind of pipette do you have? Do you have the kind where you leave a little bit in the end, or do you have a kind where you expel it all? Okay? So, and they will probably tell you, all right, which kind you have. We have the kind where you press the little lever and you do not try and get rid of the extra bit, you just leave it there. So it's always nice, especially if you have something that's not water. Like water's not such a big deal, but if you're using an acid or a base, you will want to have like a paper towel so you can put it down. Okay. Normally I would leave this on because it prevents the thing from rolling off the desk, which is kind of nice. Okay. So while I get my stuff set up, you guys can grab yourselves my cutters, my cups, and you can practice. Oh my God! If we run out of pipette pumps, you can come use one of these. They're actually meant for 25 milliliters, but it doesn't really matter. Or two.
Comes to myself. You want to?
Water. You use water. When you lift it up, when it's in the water, it should be over the line. That way it won't drop below the line when you lift it up, and then you can let some out once it's out to get it to the right level. Okay? When you're done, you can just put it away. Okay? If you're done.
No, I want to do it my
After we transfer the water, we'll just
You can just put it away now. Yep. Yes. You can just put it away when you're done. Yep, just twist it out. Yep. Thank you for cleaning up my mess for me. Put it over the sink and go like this. Hi.
You've already told me this, but can you explain to me why, when the reaction heats, the outside cools?
That's not what happens.
The container.
When the reaction heats, the outside cools. That's not, no. When the reaction produces heat, it moves to the outside. when the reaction absorbs heat and turns it into potential energy, it draws heat from the outside to the inside. So the outside will get colder.
So when it endotherm, when it gets the kinetic,
When it turns the kinetic energy into potential energy, everything gets colder. Everything.
everything.
Yeah.
And then when it's the other way, exothermic, when it goes out, everything gets hot. Wait, there was something about where it gets. I swear.
Okay, clean up, sit down.
No, you're closer to it than me.
Okay, so what we've been doing is you guys have been using what piece of equipment was that called? A pipette. Do you know what this piece of equipment is called? It's called a burette. So we were using a volumetric pipette. We are going to be reacting sodium chloride with hydrochloric acid. Okay, that's what's happening here. That's what you're going to be doing on Friday. Okay, so a couple things that you should know is before you use this, what do you imagine has been in here before you used it? Other stuff. Do you trust the students who came before you to have done a good job washing it? No, absolutely not. So I have a little beaker here full of water, and I'm going to rinse it. Now, when I rinse it, I want the burette to be closed, because otherwise it will drip out the end. Yes? This direction is closed. This direction is open. Perpendicular to the burette is closed. Parallel is open. If you find that this is either too loose or too tight, like if it's really sloppy, you can tighten it up, do righty-tighty, okay? If you find it's too stiff and you can't move it, you can lefty-loosey, okay, on the little blue thing there. All right, I think this is a little bit lefty-loosey, so I'm gonna righty-tighty it, okay? Now, I need to rinse this. So I have here some water, and because it's water, I don't even really need a funnel, because if I spill it on my hand, do I care? No, except that I do want to show you one thing that can happen. So I will get a funnel. Okay. And I want you to watch closely for what happens when I fill this thing up. Uh-oh. What can you see up here? There's still water, and it is already full. It is entirely possible to overfill this if you just dump stuff in here, because it takes a while to move up and you won't realize. So try not to overfill, because otherwise, woo, thank God that was water and not acid or base, right? All right, so when you're rinsing it, now if you were doing this in university, they tell you to rinse like 3 times with water and twice with your solution. We're not going to do that. We'll rinse once with water and once with our solution, okay, because we don't have time for that, okay? You can let it drain through the tip. That makes sure the tip is drained, but waiting for it all to come out is going to take forever. Can you think of another way to get the water out? Yes, you can do this, and you can make it go faster, because once it is turned over, you can do that, and it makes it go a lot faster if you open it up. It prevents the suction from holding it in, okay? Now, that's with water. You can fill it up all the way, empty it out all the way. But now we're going to rinse it with sodium hydroxide. Now, my question to you is, how do I know that this is sodium hydroxide? I don't. Oh, well, actually, I do, because I specifically put it here. However, if you just have a random beaker of liquid on your desk, this is my water, this is is my sodium hydroxide. How do I know which one is which? Because before I put things in there, I will have done what? I will have labeled it, because not labeling your beaker is a good way to get things wrong. Okay, so this is my NaOH, and it's not writing on here, so I'm just going to scribble on it in purple and know that that's NaOH. Okay, and I would do a better job in the future. Okay, why do I now need to rinse this with the sodium hydroxide solution? Yeah, otherwise I'm going to be diluting my sodium hydroxide with the water that is already in there. Yes? I'm going to use the funnel for this, yes. And I do see a little bit of water still left, so I'm just going to try and get rid of that. Okay, yeah. All right, so now here's my funnel. I don't want to waste reactant, though. It's a pain in the butt to make this stuff. It's expensive, blah, blah, blah. So I'm only going to add about 15 milliliters. Okay, now you would not believe the amount of times students here add about 15 milliliters and they grab the pipette and they're like, oh, I'm going to measure out. So careful. They measure out 10 milliliters and then they put it in here, and then so careful. They go halfway up here and then they put it in here. It says about 15. You know how you do about 15? You go, a milliliter is about this much, about 1 centimeter. So if you fill it to about 15 centimeters, you're good to go. So this is how I do it. I go, oh, it's about there-ish. Right? Oh, which one is this? It's got the purple scribble on it. That's my sodium hydroxide. Does it have the purple scribble? Yes, it does. Okay. I'll give you guys masking tape so you don't have to do purple scribbles, okay? Oh, and look at that, it's stuck. If it gets stuck, lift it up, okay, and it will drain. All right, and even you can even like hold it a little bit so that doesn't happen in the first place, but that's up to you. It often doesn't matter. Okay, and do I have my about 15 milliliters? Maybe not quite. Oh, that's probably a little bit more than I needed. Which part should I make sure gets rinsed next? The tip, okay? Let some run through. There we go. Now I want to dump this out in a fashion that makes sure that all of the edges get rinsed with the sodium hydroxide. Yes. I could shake it a bit. Come on in. Woo! Who are you here for? You have no idea? Okay. Devashri, it's for you. Career Center. All right. You could shake it, but like I don't like shaking, okay? Because that involves like sodium hydroxide being moved around. Don't put your thumb over the top because now you've got sodium hydroxide on your thumb. What you can do instead, and you would do this much closer to the sink. I'm doing it from high up because that way you can see what I'm doing. Otherwise in the back you won't be able to see. You sort of just basically turn it on its side and you roll it as it drains out. Okay, and you can do it even slower than that, okay? And that will coat all the sides, and then you can do that, and there we go. All right, so that takes care of that. It's been rinsed with water, it's been rinsed with sodium hydroxide. I'm now going to fill it with sodium hydroxide. Here I go. Now, this is another thing that I see people doing. All right, they're like, oh, right? What if I'm trying to fill up here? What should I do? I could use a stool, but you guys don't all have the nice little step stool I do. Should you stand on your chair or the table? No, don't stand on the chair or table. What should you do? Bring it to you, because you can hold it at whatever height you want it to be. Yes, so bring it down to you. If you're really tall and you're lucky, you might be able to have it there, but I certainly am not. The curse of tallness. Okay, and then you can fill it up. Pretty much to the top. Except for that I didn't get enough, so I'm not going to fill it to the top, but that's okay. All right, because I don't really want to waste that much reactant anyway. It doesn't really matter where you fill it to. Because when you're reading a burette, do you remember how a burette reads? This is 0, this is 50. So if you start at 10 and you finish at 16, how much was dripped out? 6. Yes, so you don't do any fancy like subtracting from 50 nonsense. People always are like, oh, start at 0, I must take my number and subtract from 50. No, why would anyone do that? You want it to be something you can just read. They're not going to make you do that. So just read the number. Just remember it goes 1, 2, 2.5, 2.6, 2.7, like that way. Okay? I right now have a big, huge air bubble in here. Okay? If you could see it, you would notice that there's like air, and then there's water, or sorry, sodium hydroxide, and then there's air. I'm going to let it drip out. Before you start your experiment, you're going to have me come over and check for air bubbles. The reason you're going to do that is that sometimes they hide, like right up in there, and you're not used to looking for them yet, so I will help you spot them, and I will help you get rid of them. One way to get rid of them is to quickly flick, 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 and sometimes you'll see them come out. Sometimes that doesn't work, in which case you will call me over and I will help you by bashing on it a little bit. You will not do that, because if something goes wrong, I want it to be my fault and not your fault. Yes? And you'll look at me and you'll be like, oh my God, I can't believe she did that, but it's okay. So this is all set now. And I need to read my initial volume. You are going to get yourself a burette reading card. And you probably won't remember this, so you're going to ask me for a burette reading card lesson, like a little mini lesson, like the parafilm mini lesson. Yes? Because I'm going to put this approximately, I'm going to put it behind. See the magic burette reading card? It is a white card with a black line on it. So fancy, fancy. You can make it anywhere. The reason you do this is because the burette is clear and colorless. The water is clear and colorless. The sodium hydroxide is clear and colorless. It is really hard to see exactly where the meniscus is. If you put this in behind, the black should go below the meniscus. Where does the black go? Below the meniscus. So you put it behind with the black below the meniscus, not behind, but below. And you make sure you're at eye level with this thing. And if you're not at eye level, what could I do? What if it were up here? I can't get myself to eye level. Bring it down, okay? If you need to bring it down, bring it down. I'm going to measure this, and I'm going to show you what it looks like, and you're going to dredge back into your summer assignment, and you're going to tell me what this measurement is to correct these things. 17? Yes. Okay. That's 17. That's 18. I've done a bad job here. There we go. That'll be 18. There we go. And the water level is. So I would like you to tell your partner what that measurement should be. First of all, does our number start with 17 or does it start with 18? 17. Is there anything after 17? 17.7. 0. Why do I need that extra 0? Yeah, we know the first decimal point, right? We have markings for that. We have to estimate the second decimal point. And we would call this our VI for initial volume. Okay, I for initial. And what have I forgotten in my measurement? Units. Okay, so there we go. That's milliliters. Now, I have pre-done this because I didn't want it to take too much time. I rinsed the pipette with water, and then I rinsed it with the hydrochloric acid because I want my other reactant in here, yes? And how do I know this is hydrochloric acid? I didn't actually label it, but I put it on that corner. But yes, we should label it. It should AHCl. This one says HCl, so it's okay. It just doesn't have a scribble. Okay. I don't know what's wrong with this sodium hydroxide beaker. Like it's not writing very nicely. It's just awkward. So I have put the 10 milliliters of HCl. 10 milliliters HCl. And I have put it into, what is this? You guys know the name of that? It is an Erlenmeyer flask. Okay? Erlenmeyer. That's Oscar Mayer. So, if you have trouble spelling it, all the vowels are E's. Erlenmeyer. Okay, Erlenmeyer. Also known as a conical flask, but you won't hear it referred to that very usually here. They do that a lot in the UK. They refer to it as a conical flask, but over here it's Erlenmeyer. I don't know why. It'd be easier. So now what I'm going to do is I am going to add phenolphthalein. Phenol, it is indeed an acid-base indicator. And I love it because there's a silent PH in the middle of the word. Phenolphthalein. Okay. If you want to talk like Sylvester the Putty Cat. Okay. Now, phenolphthalein turns from colorless to a light pink. Now, I'd like you to imagine a light pink color against a black background. How easy is that to see? It's clear and light pink. How easy it is to see against black? Not easy. So what you're going to do is underneath your flask, you are going to put a piece of paper towel. It prevents drips, which is always nice, but really the reason for doing this is to make sure that you can see the pink color. Did I actually add my phenolphthalein? No, I didn't. And if you don't add the phenolphthalein, nothing will ever happen and you'll be sad, okay? So I've added 2 drops. You may notice you get a little bit of cloudiness. That's because phenolphthalein is not super soluble in water. There's a little bit of alcohol in here to make it dissolve better, but it will usually disappear when you swirl it, okay? Here we go. And I'm now going to show you swirling and dripping simultaneously. When you go to university, you are going to be doing these on your own. If you cannot swirl and drip at the same time, they will look at you like you are an idiot, okay? Like your lab instructor will be like, what are you doing? One of you does this, one person, okay? You don't even get a lab partner for a lot of it, so, right? So, I will show you swirly drippy in a little mini demo for you at your own desk. But You swirl with your dominant hand. If you are right-handed, you pick up the flask with your right hand. Which hand will you hold your flask in? If you're left-handed, you said left. If you're right-handed, you said right. Okay, so I got it in my right hand, and I'm going to drip with my left hand. Now, once again, I'm going to stand up here so you can see. This is counterintuitive. You would normally think, oh, left hand, oh, yes? No. Not like this. No, no, no. No, 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 no. Now, the reason that you do this is it gives you a lot of stability. Okay? And what I'm going to do is I've got this end in a pinch. And like I said, you'll not remember this by Friday. Call me over. I will show you again. But this gives you a general idea. You're going to pinch here, and then you're going to put 1 or 2 fingers on the top and 1 or 2 fingers on the bottom, depending on what's comfortable for you. You tilt forward. It's like a gas pedal. Forwards is on. Backwards is off. Forwards is on, off, on, off. I tilt it forwards, off, on, off. And this gives me a really great deal of control. Okay? My initial measurement is now wrong. I don't care. Okay? Whatever. So I now put it in here. Again, you won't remember this, but I'm going to show you. Thumb and 2 fingers. Thumb and 2 fingers. Up at the top. The other 2 fingers go on the back. Whoa. Yeah, so I got my thumb and my ring finger and my pinky on one side, and then my pointer finger and my middle finger on the other side. And you don't know. This is gonna, like, I had a student write me from university on my Facebook, and she's like, we did 15 titrations in a row today. If you do this, your shoulder will be incredibly sore. You don't even want it to be a wrist motion. That's too tiring. Finger motion. It doesn't, if you're right-handed, it will probably go clockwise. If you're left-handed, I'm guessing it goes counterclockwise. Okay? It doesn't matter. But again, you'll forget that. Call me over for a mini lesson. And now we drip. Drippity drip. And if you want to come closer, you can come closer. Come closer. Come closer. Do I have to yell at you?
I want to see the pink color.
You see the pink coloring? Okay. I don't know why this is like dripping so slowly. I've never seen this. Usually it's in a stream. What's wrong with it? Ooh, hang on. Don't move. What's this? It's a water bottle. There is going to be some on the outside. I can actually, well, actually, I should do it like this. I should fold it up. But I can rinse it off. And there's going to be stuff on the side. I can rinse the sides down. Okay? Rinsing is important because otherwise all of your material is not going down into the main mixing area. Okay, so here we go. And like I said, I have no idea what's wrong with this thing. I don't know why it's dripping so slowly. I think there's a misalignment with the hole in the hole. Normally it's much faster than this. Okay, hang on. If you add too much, you'll get the color of shame. Okay.
What is the color?
Where did the color go? Oh my God. So what's happening is that right where it is, you have a high concentration of the base, and base turns it pink. But then the base, the NaOH, reacts with the HCl, and now it's gone, and now you have water. And you still have excess H plus ions, right? Let's see if I can realign this or make it. Oh my God, I guess we're stuck with drip by drip. You will be like, okay, I want the drip by drip one, because when you get to the end, you actually do want to do it drop by drop. But the first time you do it, you can actually like just kind of let it go. Okay. That's the color of shame. That means you've gone too far. Okay. Now your color should last for 20 seconds, and you do see it is fading. So this is not like the end of the earth. This was actually not too bad. If I'd added a bit more, it would have been too much. Okay. This is actually the color you're aiming for, this lovely light pink here. Okay. And then I would measure my final volume, and now I would know the volume. This one, we know its concentration. We now know its volume because we've measured the difference. We can calculate the moles. We know the stoichiometry, so we can calculate the moles of HCl that were in here. And then we can calculate the concentration of the HCl because we know its volume. We know we put 10 milliliters in there. Is good?
Is good.
Okay, go sit. Thank you.
Oh wow, really? I didn't really think you'd get it.
Okay, no, I got that one.
My tutor is gonna tell you what he
I put 95.
They're all gone. They're all gone.
Okay, this is round 2 or end of 3, right?
Andrew, we're working. Okay. Back to this, we need some quick vocabulary. Standard solution. We are on page 20. Standard solution. What does standard mean? Known. It means you have a known molar concentration. So someone has gone and found this concentration for you. And in fact, if you look at this NaOH, it says 0.0985 molar. Isn't that nice? So you will know that before you get started. Where does the standard solution go? The standard solution goes in the burette. Okay, this is our standard solution, and it goes in the burette. So for you guys, that's going to be your NaOH. Yes. Yes. So the question is, and this is an excellent question, if I add the water to this, does it not make it diluted? Right? If I add the, like if I'm like busy, right, pouring water in there, is that not a problem? Does it affect the number of moles of acid that are present? No. And it's moles that matter. Okay, the actual volume, we know we started with 10 milliliters. I don't care how much volume it's in after it's done. I'm looking for how many moles there are, and that will react regardless of how much water there is. And I know my initial volume was 10 milliliters, so I'm going to take my moles that I found and divide it by the original 10 milliliters. Does that make sense? Cool. So that's our standard solution. It is also known as the titrant. Okay? The sample solution is also known as the analyte because it's being analyzed. Yes? You are analyzing the HCl in this case. Okay? So your sample is down here. That's your analyte, and it's whatever is your unknown concentration. Okay, so your standard is known. It's also known as the titrant. Oh, I forgot to mention this little lever here. It's called the stopcock. I am so sorry for the name. No choice, that's what it's called. Stopcock. It was like when we used to have to teach the 9 planets back when there were 9 planets, and nobody wanted to teach like what's it, the 6th or 7th planet, because you're like, oh my God, I don't want to say that to a bunch of grade 9s. Lordy. Okay. Phenolphthalein is an example of an indicator. It will change when we have added exactly the right amount of standard solution to react very precisely with the sample solution, okay? Because data, how perfect is my titration going to be? Am I going to be perfect? No, I'm not going to be perfect. So if we are not perfect, how can we get better data? Yes. You could look it up online, but how are you going to look up online the concentration of a solution that we just made? Right? Can't look that up online. Yes. Repeat it. You're going to repeat it because the more repetitions you do, the less your error matters. And if you actually do some statistics on it, which we are not going to do because this is not a stats course, you can find like the standard deviations and all that kind of stuff. But we are not doing that. We're just going to take at least 3 volumes, and they should be within 0.2 milliliters of each other. Okay, that 0.2 number is arbitrary. I have put it at that because that is a reasonably achievable goal by grade 11 students. In university, it might be 0.1 milliliter. Yes? Yes. That's why your labs are 4 hours long. Probably not, because you got to be like, your chances of making an error and having to start over are much greater. Okay? Any volumes that are not within that limit are called outliers, or at least they will be for here. So when you take your average, you're going to exclude any volumes that are further than 0.2 milliliters of each other. And then you'll do your stoichiometry calculations. Okay? So here we have a little problem. You can see here, this is what we've done already today, right? We have our volume of our HCl was 10 milliliters. We don't know its concentration. That's what we don't know. We put that in the Erlenmeyer flask. And then we put our standardized NaOH, and we'll have to know its concentration because it is standardized. Standardized means known concentration. We take our initial reading of the volume. We add our phenolphthalein indicator. We add sodium hydroxide until it changes color. We measure our final volume. So now we have a final volume, we have initial volume. We can subtract those two, we find 12 milliliters. That NaOH, remember we had to have known that. It had to have been given to you. And then we just do the math on it. Yeah? La, 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 la. Are you guys good with the math? Okay. Do the math, do the math, do the math. There's a bunch of exercises here. That's your homework. Okay? Pages 22, 23, and 24. And you know what? If you don't have time to do all the questions, do the odd questions, and then go back later and do the even questions as review. Okay? Hi. How you doing?
Tired.
Tired? Yeah.
I wanted to clarify that like at a surface level, I understand. So The idea is we've got a urette filled with a liquid that we know the molarity of, and then because it's a urette, we can figure out the volume as well. Which means we can figure out the number of moles. Looking at the chemical formulas with the reactant, we can figure out what the ratio should be, and then we go until it stops reacting and it's balanced. And then once it's balanced, we can figure out, oh, how much should we add to it? So it's like if it was one where it was like 1:2 ratio, you would multiply the volume by 2.
Well, you wouldn't multiply. You would use the mole ratio. It's just a little. You could do it that way, but it's tidier to use the mole ratio.
In the end, we figure out the concentration of this. We know the volume of that.
Yeah.
We just don't know
How many moles? Yeah. Hi.
It's just gonna be like solving solving problems, or is it gonna be like definition?
Solving problems. Hi.
I was wondering, how it's like you got it till like it's a little bit pink, right?
Yes.
That means it's like slightly
Slightly
base.
basic. Yes. And here's the deal. It will change within one drop. So the difference in volume isn't enough to worry about between, haven't finished and finished. Yeah. Hi. I've not finished. Oh, you want to finish it? All right. There we go.
I won't be at school for the second half of Wednesday. I
Okay.
sent an email. I've got a checkup with my dental
Yes.
something.
Yes.
I'm not actually getting the tooth removed, but I think they're checking.
Yeah, yeah.
I've been